confusion about an explicit example that gives you a Fuchsian model for a particular Riemann surface. So I thought it's best to provide you an explicit example where I consider a pair of fans, a hyperbolic sphere with 3 holes in it, or 3 boundaries. So the idea is the following. You can start from upper half plane, and then you find one hyperbolic hexagon, which is a half of this picture. So hyperbolic hexagon is a hexagon that you draw on upper half plane, and each side, so you have 6 sides, and each side must be a geodesic on the upper half plane, and moreover every edges must be intersecting orthogonally. So that's the definition of hyperbolic hexagons. So you can start from one hyperbolic hexagon and then make a image of the same hyperbolic hexagon, then glue them. The good thing about hyperbolic hexagon is that you can uniquely fix a hyperbolic hexagon once you provide the length of 3 non-adjacent sides. So if you provide me the length of 3 non-adjacent sides of a hyperbolic hexagon, you don't have any possibilities. Like, you have one single possibility. You will get a unique hyperbolic hexagon. That's the main philosophy of constructing hyperbolic Riemann surfaces from the upper half plane. So you start from one hyperbolic hexagon, then take its image, then glue them, and then you have to find an appropriate identification that provides you a pair of fans. So the easy way to understand is the following. You start from the pair of fans, then you can draw 3 seams on the pair of fans, which connects the 3 boundaries. So you have boundary B1 and boundary B3 for the pair of fans. Then you draw a perpendicular line that connects, or the geodesic that connects B3 and B1, and then draw a geodesic that connects B1 and B2, and then B2 and B3. Then you can cut along these seams. That will provide you all the hexagons that you want. So you get 2 hexagons. So the idea is that you can obtain this domain by or you can obtain this region as a domain of some particular group that is acting on the upper half plane. So that's a group, that's a subgroup of PSL2R, and the generators of that subgroup is precisely gamma 1 and gamma 3. And what gamma 1 and gamma 3 does is the following. So you have the hyperbolic hexagon image of pair of fans on the upper half plane. So on the upper half plane you have a domain where you have several geodesics. You have a domain with edges that are geodesics on the upper half plane. So the geodesic, which I drew using red color, is the geodesic that corresponds to the boundary B1 of pair of fans. So it must have length L1, and you have another geodesic which I drew with blue color that corresponds to the boundary B3 that has length L3, and this geodesic along this geodesic. So you provide an identification. So you have 2 adjacent sides for this images, the geodesic that corresponds to B1, and then you provide an identification. So you identify this side with this side, and identify this side with this side. So the first identification is what I call gamma 1, and the second identification is what I call gamma 3. And the identification metrics are precisely the one that I wrote on the board. So what I do is I can start from 2 PSL2R matrices, and then I can form a group using these 2 matrices, which I call as gamma P, and then you can mod out upper half plane with this gamma P. That will provide you the pair of fans.
These identification matrices are identifying the opposite sides?
Opposite sides, yeah.
So each R1 identifies, it's written, R1 identifies that.
Yeah. So these are R1 or gamma 1, yeah.
And your pair of fans, when you do the cutting, it splits up into 2 hexagons.
2 hexagons.
And these are the 2 hexagons.
2 hexagons.
And they've identified a pair.
Yeah. So the idea is that you have a unique hyperbolic hexagon on the upper half plane with specified length for non-adjacent sides, and you are just taking the image of the same hexagon to obtain the hyperbolic pair of fans, right? So that tells that if you tell me what are the lengths of the boundaries of a hyperbolic pair of fans, you are uniquely fixing the pair of fans. So once you provide the boundary lengths, you are uniquely fixing a thrice.
And these dotted lines, do they go and intersect, for instance, a blue circle in its middle?
Yeah, in a perpendicular way.
Perpendicular, and the other one is halfway around?
Yeah.
Okay.
So it's like half of the. So that's why.
Hexagons are the same.
Exactly. So the point is that this pair of pan has an extra symmetry because of the precisely that reason. So you could swap the hexagon, and that still preserve this pair of pan.
The dotted lines are the white lines.
Exactly.
So the identification gamma 3 means that Z is equal to gamma 3.
Gamma 3 Z. So set gamma 3 is should be equal to, take A, B, C, D. So that's AC, B plus CC, D.
And that is identified with Z.
Exactly. So it should be equal to, so this identified with Z. And this identification provides you a simple closed geodesy, so which is a boundary geodesy.
And both gamma 1 and gamma 3 should fix that vertical line.
Yeah, yeah, that's true. So this is one of these things.
And now if you wanted to take the functions of infinity, what would happen?
Yeah, that's what I did here. So you have a general pair of pans that has a finite boundary length. Then you could take this limit L1, L2, L3 goes to 0. Then what you reproduce is the gamma p becomes the group gamma 2. So that is generated by gamma 1 0, gamma 3 0, where gamma 1 0 is given by 1 0 2 1, and gamma 3 0 is given by 1 minus 2 0 1. So gamma 1 0 is the identification that identifies C to C by 2C plus 1, and gamma 3 0 provide you this identification C going to C minus 2. So that's how you get this nice fundamental domain. So for the thrice, so at the end you are getting a thrice punctured sphere.
And what will that diagram become if L1, L2, L3 goes to 0?
So this is this diagram. So this is the fundamental domain for gamma 2.
And now I'm being very stupid, but can you explain to me how that shrinks to that?
So you could assume that your L1 is going to have
Fine.
0 length.
Yes.
So that's how you get this 0 here. And if you
What I'm not understanding is how it comes down.
okay, so the point is that this geodesic can be extended to the real axis of hyperbolic upper half plane, and then
Oh, so this line, red line was not touching the axis.
yeah, it was not touching the axis. Now it will touch the axis. So if you complete it, and then the position of this fixed point is L1 by 2, and the position of this fixed point is minus L1 by 2. So when you take L1 and L2 goes to 0, so it shrinks to a point which is becoming a point 0 on the real line, and then so you have this green line that shrinks to another point which is minus 1 and plus 1,
Yeah.
and then you have the blue line that goes to I infinity. So that's how you get this domain.
Thank you.
So now you have this folding. So you have this side identified with this vertical line. So that provides you this tube, and then gamma 1 0 perform this identification. Each boundary of each point on this circle will identify with some point on the circle. So you have this identification. Exactly. So that's how this folding provides you this particular tube, and then you have minus 1 and 1 becomes another cylinder. So this is the way you get thrice punctured sphere. So that's why I'm saying. So now you see you have a pair of pans, and this pair of pan has 3 variables. The boundary length L1, L2, L3. Once you vary L1 and L2, L3, then you are actually varying the structure of pair of pans. So you are basically changing the complex structure of a pair of pans. So once you provide the boundary length of a hyperbolic pair of pans, you are uniquely fixing the complex structure.
From the earlier talk, I took the lesson away that the modulus space essentially comes out of the embedding of the domain dynamics essentially.
Yeah.
So this expression of for the generator is
Yeah.
quite non-transparent, right? So
So-
how do I kind of know about the modulus space?
So you see, so you have the parameter for pair of fans which are L1, L2, L3, and the generator depends on L1, L2, L3. So once you vary the parameters, you are actually varying the group. Right? When you take L1 goes to 0, you are getting a particular group, which is gamma 2. So if you take L1 to infinity, you may get something else.
And this gamma 1, gamma 2 is true.
Huh? Yeah, exactly. So you take the trace, you get the exactly. Yeah,
And this gamma 1, gamma 2, gamma 3 are generators of a dot. The subgroup has more elements.
yeah, it has more elements, right? So you can just multiply. You can write any word using these generators, and all of them will correspond to different geodesics. You could have something going like this. So you have several ways of identifying it, right? So since it's not a simply connected region. Huh? Exactly, yeah. So you have only independent two generators that generates two boundaries, and the third boundary can be generated using these two elements. So because you see you have a homotopy cycle here and cycle here, if you combine them, you are basically producing the other cycle.
But the modular space of three functions here is
Yeah, so that's because you are taking L1, L2, L3 to 0.
so this change in L1 L2 L3 does not change the complex structure. In a
It
modular
change
space.
it,
L1, L2, L3 is not the three functions here. It's finite.
yeah,
To get the three functions here, you need to
Or
take
you
the
mean
yeah.
three functions here.
So this
when we have
this is a
points.
sphere with boundaries. So it's a bordered surface.
So this is conformally equivalent to a three.
No.
Enter a finite.
Yeah.
Yogi,
Huh? Yeah.
yeah, if you get finite L1, L2, L3, then what do you get?
If you
Take L1, L2, L3 finite.
yeah.
Then what after do you get?
Oh, it's a bordered sphere. So a sphere with three borders.
Oh, so you still get sphere is the border.
Exactly. Yeah.
He's drawn that on the board. You probably can't see, but it's just a three function. I mean, the Pan's diagram starts at finite length.
Yeah. Okay. I think zero limit you get. Yeah.
What?
You get a lot. Yeah. Fine.
This gamma 1 0, gamma 3 0
Yeah.
seems to be like idempotent thing. I mean, it's gamma square is gamma.
Uh,
And gamma 1 0 square is gamma 1 0 is it? I mean, it's an order 2 thing or no?
oh, sorry. I think.
Does it square to identity? I mean,
Oh,
this
no.
gamma 2, that's
So-
2 refers to what? Does it refer to the order of the?
You mean gamma 1 or gamma? Which two you are talking about?
Gamma 1 0
Oh, you-
square
okay.
is gamma 1 0.
Oh, okay.
And gamma 3 0 square is gamma 3 0. It seems like. Or not?
No, it's actually just providing an index. It has no more meaning. I just wanted to distinguish from a general case from.
Going to itself, but they are all related. I'm saying that right, it's like gamma 3 0 is string because it's Z going to the minus 2,
Yeah.
to the minus 4, then minus 6, and so on.
Yeah.
But the first one may maybe
No, are you asking gamma 1 square will it become identity or?
some gamma 1 0 to some power is that identity. Is it coming back to itself or I?
Oh, okay. So maybe what you can do is you can go from here and then you can find an identification to here, and then so you have to do several combinations. So it's not gamma 1 0 square won't give you. So it's like generating windings.
So what's this? Okay.
So it's basically providing you windings, right? So if you square it, so you are going twice. So this is an explicit example. So you could see that you start seeing some numbers, and you start getting some moduli space, right? So things are becoming more transparent.
Just to answer Joseph's question, this gamma 2, this 2 there, usually stands for element of the identity where C is the 2
Exactly.
morphism.
Yeah. So that's the definition of gamma 2. Yeah.
So these fiction subgroups, do they always represent, are they generated by single dimension?
No. You could have more. So this is a simple example. I mean, for this is
Can I see the number of generations?
you could look into how many number of independent cycles are there, right? So because you will be able to generate all cycles by using some basic cycles, right? So these generators can be mapped to each independent cycle on the surface. So in that sense, you can count it.
Luigi?
Huh?
Yeah, can I ask something?
Sure, sure.
Normally, so you are taking the upper half plate
Yeah.
divided by this quotient group. Right?
Yeah, yeah.
Suppose we know anything about that polymer or something, okay? But just take upper half plate divided by the quotient group.
Yeah.
Then the only boundaries are either orbifold point or the boundary of the orbital line, right? Because otherwise the geodesic can keep going.
Sorry, I couldn't get the last.
And then, suppose you have upper half plate bordered out by some blue key.
Okay, which is not subgroup of PSL2R.
No, this is a subgroup of
Oh, okay.
Okay?
Yeah,
Then I'm saying the normal you have to make such quotient
yeah,
and take a geodesic,
yeah,
right? The geodesic can be continuous, right?
yeah,
Beyond those boundaries.
Yeah.
The geodesic either ends at a orbifold point or at the boundary of the original line.
exactly. Yeah, yeah.
So I'm a little confused about where these holes are coming from, right? I mean,
See,
we have taken this PL2 for finite L1, L2, L3.
yeah, yeah.
I mean, because you could continue the geodesic, right?
No, actually, you can't. So the point is that you can't get a hyperbolic pair of spans with boundaries with finite length from a thrice punctured hyperbolic sphere.
Ashok,
So
can you see his diagram? Can you see the first diagram?
Yeah, I can see the diagram. I'm saying suppose you forget about the polygon, okay?
Ah.
Then, I mean, there is no reason why the geodesic has to stop at the boundary of the polygon.
Yeah, because on the
No.
diagram you can just very,
No, but you know, in the diagram, I don't think the red, green, and blue lines are not identified with anything else.
Yeah.
Those are genuine boundaries of that figure. Everything else is identified with something else.
Okay, so suppose you didn't have the boundary of those figures, and if you let it just keep going.
Yeah. So the point is that
Then
if
you could keep, yeah.
yeah. So the point is that the geodesic will just land on the boundaries perpendicularly. So if you are continuing it, the fact that this is a hyperbolic surface will make the boundary a hyperbolic annulus if you try to continue it.
Okay, then.
So it won't end up in, it won't go to a puncture. It will just continue if you want to continue it.
Okay, yeah. So suppose you have a continuous, then what happens? You have to say it just goes out, is it?
Yeah, it just goes.
Okay.
The only condition is that on the boundaries, they should land perpendicularly.
So the geodesic, right?
Yeah,
On in the tower,
yeah.
where do they end up?
Oh, they end here, right? So,
No, but suppose you want
The
the
red line, same with the geodesic.
oh, you can continue it.
Yeah.
Geodesic.
Oh, this
The
geodesic.
geodesic.
Oh, okay, this one, right? So you want
Yeah.
the seam, right?
Yeah.
So this will end up on the real axis with some fixed point. Yeah,
Okay, so that sort takes is what? For this particular choice of suppose to choose gamma 1, gamma 2, gamma 3,
yeah,
and keep it continuing the geodesic.
yeah.
What is that?
So if I continue it, since you have an identification here, some point out of the fundamental domain will be identified to some other point on the inside the fundamental domain.
This boundary is not identified with anything else in this diagram.
So that's true. Yeah,
So you can keep going.
yeah.
Unless there is some other identification of this.
Oh, so the point is that
and then it is the boundary of the
Yeah.
yeah. So the only thing which I can imagine is that you could add a hyperbolic annulus here, which will just go up to infinity.
Infinity, but infinity is a point.
Right. So if you continue the that's true. If you continue the geodesic to the real axis, that's like getting a geodesic having infinite length.
Okay. So you are
Right.
saying it will go to the real axis and then it has the
It ends there.
interpretation of the open boundary.
Yeah, that is true.
Oh.
Yeah.
Okay.
So that's why I'm saying it's like attaching a infinite hyperbolic annulus here.
Okay. Okay.
So it won't go to a puncture.
Okay.
I mean, you could think of boundary of hyperbolic annulus as some sort of puncture, just like cylinder.
Okay.
So if I don't know what surface I'm constructing,
Yeah.
I take some group, let's say those elements,
Yeah.
I portion it out, look at the fundamental domain,
Yeah.
And now my job is to interpret that domain as
Some particular, exactly.
So in that step,
Yeah.
how do I interpret what edges are the boundary edges?
Yeah, so your identification group itself will tell you which boundaries you are supposed to identify. Right? So here the identification group, one of the element in the group is the one which is telling you you are supposed to identify this. I'm not making any pre-assumptions that I should identify these
Some
two.
other fundamental domains.
Yeah. Yeah.
Their different edges will be identified.
Yeah, that is true. So then it's the elements which are telling me how to identify.
So does that mean in another fundamental domain, this portion might as well be interpreted as some other?
No, you want no. It will be unique surface. So you could take a fundamental domain that belongs to this region. So that fundamental domain will also have some identical identification, so that you at the end you get the same surface. So you could take any fundamental image of fundamental domain.
Wait, but just to make sure I understand, this surface that you've drawn with the finite pair of lines is generated not just by the generators, but also some lines.
No, it's just by this generated by just by this.
So the generators first identify the white with the white,
Yeah, and here.
but for instance, a red line, how did that come?
So red line is this one, right? So if you identify this, so this boundary is identified with this. So
Yeah.
the boundary of the red line also will get identified.
So how do you know that the red line?
Oh, is actually here.
That's the minimal length.
Yeah, that is true.
That's the minimal
That is
length.
a minimum. So here actually I use this condition that things should be perpendicular. So that
Yeah.
fixes it.
Yeah, so but it's not just identification. There's an extra rule saying that you cut that
Yeah.
surface.
Exactly.
Yeah.
That perpendicular.
Yeah.
That is true.
So this cut surface is not generated just by an identification. It's identification plus some rule.
Exactly. So that's something called Neal's extension. So I didn't want to really.
But it's only these compact Riemann surfaces that are generated just by identification.
Yeah, that's true.
The Riemann surfaces with mark points are generated
Genuinely by identification.
identification.
Yeah, that's true. For if I'm looking into have some hyperbolic pair of points or some pair of points, then you have to provide me this rule that the geodesic along or the curve along which I'm cutting the surface must be the minimal length one.
Yeah.
So that's an extra rule.
So identification plus cutting.
Exactly.
I don't understand. So there won't be any fundamental, any other fundamental region in which you have the identification from these colored edges?
No.
No?
No. Because that has a specific length, right?
But Ruby, algebraically, these essential elements which you wrote down,
Yeah.
is there some algebraic way of, and what I mean is that, okay, I can see what you're doing with geometry,
Yeah.
but is there a classification of the essential elements
Yeah.
which will do the job
Yeah.
of
It is there, yeah.
giving it edits?
Yeah, so actually that's the way this whole subject started. I think Fengel and Nielsen, in their book, so that person who wrote, Fengel didn't actually complete the paper. So he died before writing the paper. Then one of his friends wrote a book on it, and the book does not have any single figure. It's just group theory. So it's actually after the work of Wolpert, things become more geometrical.
But sorry, maybe a related question. From the answer to Ashok's question and to the discussion, it seems like there are some subgroups of suppose we don't know further cutting, just identify. Some subgroups generate compact Riemann surfaces with mark points,
Mark point.
and some subgroups do something different.
Yeah.
So how do we know which subgroup generates only compact Riemann surfaces?
So you have to just look into the elements in the group. So if you are able to find some parabolic element, that means you are having the punctures.
Those are punctures. Punctures I'm fine with, but I
Yeah.
don't want these like open-ended surfaces. So what is that? Is there something like an elliptical element,
You have an elliptic element.
and that's we don't want?
Yeah, you can consider such surfaces, but in my case, I don't want to discuss.
So is it right that if you have only what is it hyperbolic elements,
Yeah,
you get compact Riemann surfaces?
yeah,
If you have hyperbolic and parabolic elements, you get compact Riemann surfaces and mark points.
mark point.
And if you have hyperbolic,
Uh,
if you have
uh,
at least one parabolic element, you get something weird happening.
Yeah,
So there was a parabolic element in this too.
So that's what I took. L1 goes to
Elliptic, sorry,
elliptic. You can write down, but I didn't really bother to write.
And then after that,
But is it true that the example had an elliptic element?
No, in this one, no.
But then I don't.
yeah, I don't understand. Because I thought this was an example of a weird case.
No, it's actually not a weird. I mean, you have separate elliptic elements in it.
No, but you have, there exists in the whole group, there exists an elliptic element.
In this one, no.
No, but then it was not generating a compact Riemann circle.
No, it is generating, right?
No.
Because the
without
you know the point is that you are cutting using the fundamental domain. So the fundamental domain, to get the fundamental domain, you don't have to use any cutting rule, right? The fundamental domain is uniquely fixed. You could just take the upper half plane and then give me this group and put it in a computer. The computer will generate this particular region.
That fundamental domain, how do I know that this is not giving me some geodesic output?
Because the group elements tells me that what are the identifications that I'm supposed to do.
Wait, but in answer to Ashok's question, you said that if you continue that geodesic past the red curve, it would end on the upper half plane and then like a boundary. Right?
Yeah, that's true. So if I want to do that, but the point is that I'm supposed to.
Suppose I'm not allowing you to cut, I'm just identifying.
So, but the point is that my
The fundamental domain he already did
already,
that.
yeah,
And then there was identification. So the red curve was also present in the fundamental
Yeah.
domain. And once you identify, you're bound to get something with holes.
that is true. That is true.
It's not additional.
So it's not. So the point is that additional information in some other sense. So for generic situation,
Wait, are you saying that you didn't need to specify a cutting rule?
no. From here, if you want to get the surface, you don't have to tell me or give me any cutting rules, because when you the story is similar for the torus. So you get this fundamental domain, right? You could have continued to here, right? When you do this identification, so the identification itself is telling me that I am supposed to just restrict to this domain.
No, if you but the end of a curve is not identified with something, it's a boundary.
That is true. So if I, so I think in that,
If all edges are identified, then you get something compact.
yeah,
But if identification is not in between all edges, then the remaining ones have to be thought of as the boundary of that surface.
But how do you know where to draw the boundary?
So that's a fundamental domain.
Meaning meaning a point below there is identified with something else.
Fundamental domain meaning, that is, there is no further identification in the one.
yeah,
No, which means if I go a little bit below the red point, is it identified with something else?
Yes.
yeah.
With something else where? I mean, within your surface or outside? Within, but then it's not a boundary.
But somehow that.
It seems that you need enough
Yeah.
number of group elements to identify all the edges. Right?
Yeah, that is
So
true.
it's not just a question of elliptic or hyperbolic.
Yeah,
That somehow the group has to have enough elements
To do the identification.
all the
yeah,
edges, right?
that's true.
So I can imagine that if you have a four-function, here is 4 holes,
Yeah,
which will generate some elements. If you add some more elements to identify your holes, then you get a compact surface.
that is true. So if you include that extra identification, that becomes a torus with one hole, right?
But at the
Yeah.
moment,
At the moment, it looks like, I mean, I agree with whatever Shiraz is saying. So, I mean, like what Ashok was saying, so you could think of, you start with two identifications, and then you can find which, how that particular identification is identifying some geodesic on the upper half plane, and then think that, you see, that's equivalent to saying that forget about these boundaries. And then what you have is these geodesics, right?
Fundamental domain unambiguous.
Yeah, that is true. That is true. So I'm just trying to say that if I don't include this boundary, it's more like saying that you have a hyperbolic pair of spans, and at each boundary you start getting annulus.
so just keep going, but that ends like with a big hole.
Yeah, if I just want to continue, blindly continue from this one, just by forgetting about the fact that there are so many other elements, here you see, here I am just worrying about two elements.
I just want the whole surface. You do all the identifications with all the elements generated by this subgroup.
Yeah,
What is the final surface? Is it
The-
compact or not?
it's actually compact.
Okay.
No, it will probably not be compact. Because does it look like it's compact? Because
See that-
saying that these,
See the
geodesic, these are bound.
The rule is just like this. So you can think of you have a long cylinder, but if you once you want to make a finite a cylinder having finite length, you are basically like what Shiraz is saying. You are providing you a cutting rule, right?
Yeah.
You are restricting your fundamental domain to something.
Suppose you have a splitting.
Yeah.
Suppose let's say complex state, right?
Yeah.
If you just order by translation along the x-axis,
Yeah.
you get a cylinder, not a roller, right?
That is true. So that's
you have to add sufficient number of group elements to make it compact,
yeah.
right?
Yeah.
So there must be some condition that the group must be sufficiently big.
That is
all
true.
the identifications are necessary to make it compact are taken care of.
That is true. So that's why if when you have boundary, so if you are not cutting along some geodesic on the edges, you are basically you are continuing your surface to infinity. So you are chopping off some region, right? It's just like how you get a cylinder having finite length from an infinite cylinder, right?
Sorry, but the L1 boundary was decided by the two generators that you
Yeah.
wrote down.
Yeah.
No, I think not.
Yes, because
No, I mean, the endpoints were, but the boundary itself was just arbitrary. I mean, by the cutting rule, that's what I am.
So the point is that the boundary, so the identification does a lot of things, right? So the identification identify each point on the two geodesics. But then your cutting rule is that you should cut along that geodesic which has minimum length. That connects to these identifications.
Look at
So-
that. The hexagon was specified by L1 and L2 and 3. And those, L1 specified the bottom thing, and then the next two things and on, and then that specified those curves which were generated by Kruger. But the fact that you ended this whole curve here at L1, that I thought was a supplementary rule.
Exactly. So actually hyperbolic hexagon, the way you get the hyperbolic hexagon, there itself you have this rule. So you provide me two geodesics, and then tells that you want a geodesic connecting these two geodesic which has minimum length.
so is the fundamental domain the single hexagon or this copy of two hexagons? Or more?
So it's the copy of two hexagons.
That's the fundamental domain.
Yes.
Once you-
So
Even if you forget everything, just ask what happened, what is the fundamental region of upper half plane divided by this group, you get that.
Do you get this or do you get more?
no, the point is that so if I'm just using the identification, I'm supposed to extend it, right?
I think you get more.
You are supposed to take the geodesic to the real axis.
Wait, so you wrote gamma p. So
Yeah.
you take PSS over modulo, sorry, the upper half plane modulo gamma p.
Yeah.
What is the fundamental domain?
So maybe so if I want a pair of
The
pens,
cutting rules, it cuts you down to.
so that's why I said you have to start from hexagons, right? So I started from a hexagon, I mean to just give you the feeling, and then I'm thinking of the boundary as some minimal geodesic connecting these different geodesics.
In particular, if we give something that identifies the top with the bottom,
Yeah,
then it will be like doing these two boundaries.
yeah.
You will get a torus boundary.
So in this picture, when I say fundamental domain, it means a fundamental domain with respect to this pair of pens.
So only, see, the element is different, right? Because in the compact case, the elements were such that the fundamental domain didn't even touch the thing. In the parabolic case, it was such that the fundamental domain just touched the thing.
So the
Now here it's going all the way down to the.
no, the parabolic element is not actually this one. The parabolic element that you are talking about, or the the hyperbolic element that you are talking about is doing an identification across these places, right? So once you come down, they have a finite length. So the fundamental domain, in the naive sense, it should be something which is landing on the real line. But once
In the case of compact surface, that doesn't happen, right? The fundamental domain doesn't even touch the real.
that is true. So the point is that there you are providing me another rule, that how you chop off some of the
So
boundaries.
it seems that the fact that the fundamental is qualitatively different
Yeah.
means that there is something different is going on, some new type of thing there, right?
The trace of both of these guys was
So the what I understand is that an element is identified with a minimal length geodesic that is lying on some part of the surface. It's not precisely telling you about the boundary. Right? Now, when you think about, so it's an extra rule in that sense.
Sorry, but just to ask again, one of the questions that came up was, given the subgroup,
Yeah.
how do I know how do I know whether it is compact or not? Is there a clear answer to that?
So it's you see this fundamental domain like this, but still you could. The extra rule says that you have to always make the.
Suppose I have just identified no extra rule. With that, I want to know whether the surface is compact or not.
Oh, in that sense, you blindly if you're doing, you get some surface like this, right?
And
So that this doesn't look like a compact
is there
surface.
an algebraic characterization of the group
Yeah,
that tells me
that's what the question.
whether I get a compact surface by pointing out that group, just by pointing out.
So what I understand is that they just say, oh, you have to just look into the elements and see whether all elements are hyperbolic or not. Then you are supposed to have this particular cutting group.
But Ashok also had a complex, like the cylinder thing. It
Yeah.
also has to be enough.
Yeah. See, I think that is not probably completely true, because suppose you have a group, right, where all elements are hyperbolic.
Yeah.
Okay. Now you remove one derivative of the group. Still all elements will remain hyperbolic, right?
Yeah.
But
That
now
is-
that you have lost the identification, it will probably reach the boundary. Right?
It will?
Because see, once you lose one identification,
Yeah.
suppose you remove a group element.
Yeah.
Right? Then if you lose the identification, then the boundary will again keep extending, right?
That is true.
So it's not just the statement of whether all elements of a group are hyperbolic or not.
Yeah.
There was something more which determines whether a group generates a compact Riemann surface or
See the.
not, right?
As far as I understand, in this picture, you only look into the length of each geodesic. If you can find a geodesic on the surface that has infinite length, then, I mean, in this
Then it is
picture,
not compact.
yeah.
Fine. Okay, let's move on.
I think that, I mean, you,
The security will never be there for surfaces with mark points.
Yeah, with mark points you exactly
It's always
always end on the real. Yeah, that's true.
The only infinite length you will use.
Yeah, so now, so we understood what is a Fuchsian model of a Riemann surface. So you can generate Riemann surface with punctures or boundaries. When you, if you want boundaries, you have to come up with this extra rule that the boundary, on the boundary everything should land perpendicularly. Precisely that's the thing which gives you this cutting rule.
Okay.
And then you have to understand, see what was the main motivation for discussing all this model. The main motivation that was that we want to compare the complex structure of two Riemann surfaces to understand the moduli space of Riemann surface. What are the possible Riemann surfaces that you can have? So to understand this, so it's extremely useful to introduce this notion of quasi-conformal transformation. So we have a Riemann surface that is characterized by complex structure, and to describe the space of all possible Riemann surface, we want to compare the complex structure. So the idea is that you want how two Riemann surfaces can be related to each other. So for this, we have to introduce this notion of quasi-conformal transformation. So let me define what is the definition, or what you mean by a quasi-conformal transformation. So you can consider a domain, a simply connected domain, and in that domain you define a function f c c bar. So z and z bar are the coordinates on complex coordinates on this domain D, and then the function f has a following property. The property is that in this domain, this function should have a well-behaved definition for del f del c bar, and then del f del c. You want nice behaving derivatives. You don't want del f, it's not necessary to have del f by del c bar equal to 0. Once you put that condition, that becomes a holomorphic function. So it's a generalization of holomorphic function, and moreover it has to satisfy one more property. So the property is that inside this domain, if you compute the mod of del f by del c bar, then it should be less than or equal to some real number k into mod of del f del c, and where k should be less than or equal to 0 and 1. It should be a number, real number, that belongs to this interval 0 and 1. So if the function satisfy all these properties, then we call this function as quasi-conformal transformation. This is just a nomenclature. It's just a definition of one class of functions, and these functions are really useful. The main reason is that we are putting a particular constraint on this function. So del f del c bar must be less than or equal to k into del f del c, where k should be less than 1. This implies that we have del f del c mod square minus del f del c whole square is greater than 0.
One of them is del bar.
Yeah, so yeah. This means if you are mapping a domain to some other domain using this quasi-conformal transformation, it won't change the orientation of the surface. So you have a Jacobian that is greater than or equal to greater than 0. That means this transformation won't change the orientation of the surface. So you start from some surface, do a quasi-conformal transformation, you get another surface that has same orientation. Because in the definition of Riemann surface, we are fixing a specific orientation. You don't want to consider those mapping which change the orientation of the surface. So if the Jacobian is equal to 0 or less than 0, that's basically changing the orientation.
Jacobian f bar, I mean, why is this Jacobian?
See, in terms of C and C bar. So in terms of C and C bar, you can define an orientation, right? It's like with respect to x and y, how you
I thought Jacobian was determinant matrix del f del z, del f del z bar, del f bar del z, del f bar del z bar.
so that's why it's mod.
And
Right.
then that.
Yeah. So so let me give a simple example of a quasi-conformal transformation. So you can look into an extended complex plane or the complex plane and divide the complex plane into two. So one example of quasi-conformal transformation is this. C belongs to H, and x plus I ky with C equal to x plus Iy, and this is defined for Z belongs to C minus H. So here you have upper half plane and here you have lower half plane. So you are defining a function that behaves differently in the upper half plane and lower half plane. So the lower half plane I denote by H star. Now you can compute the this object del f del c bar, take the mod and divide del f del c. You could easily see that this function behaves as a holomorphic function on the upper half plane and a proper quasi-conformal transformation in the lower half plane. So you get k minus 1 with k plus 1. Here I assume that k is greater than 1. So this is an example for, so this is always less than or equal to less than 1. So this is an example of a quasi-conformal transformation. So this is the definition of quasi-conformal transformation, which I gave you only for a simply connected domain. You can extend this definition to some more complicated domains, and then assume that you have such a quasi-conformal transformation. So the good thing about quasi-conformal transformation is that using a quasi-conformal transformation, you can go from any Riemann surface to any other Riemann surface having same topology.
So this x plus I k y is some kind of linear combination of z on z
Exactly.
bar
Yeah.
with less of z bar and more of z.
Yeah, that is true. So that's why, so you're always keeping C bar less. So that's why you're not changing the orientation. If you make the C bar more, then that's actually changing the orientation. So let me define what you mean by the Teichmuller space of Riemann surface. So my definition will always depend on a base Riemann surface. I start from a particular Riemann surface, and that base Riemann surface you can choose arbitrarily. So let me start with some arbitrary Riemann surface, and then I consider a pair SF. So by this, what I mean is that I can get surface S by performing a quasi-conformal transformation F on R. So you can start from Riemann surface R and then define a quasi-conformal transformation on R, and after the quasi-conformal transformation you get another Riemann surface S. So
Patch by patch
you do a mapping, exactly. So here I
This F is related to Beltrami stuff.
yeah, so that's what. So the Beltrami differentials and this quasi-conformal transformation are not precisely same, but you can find a one-to-one mapping given there is some particular normalization. So you have a pair that you are defining. So this pair, all of these pairs are not different. So you can consider two pairs S prime, F prime, and SF. So these corresponds to two different Riemann surfaces that you can obtain from a same Riemann surface R. So you say that these two pairs are same, provided if S is a Riemann surface that you obtain after performing the quasi-conformal transformation on Riemann surface R. And S prime is another Riemann surface that you obtain from R by doing another quasi-conformal transformation. So if you are able to see that F prime same, exactly.
But if not, then you can move around.
Exactly, that is a definition of equivalence. So if F prime, F inverse, so this is a mapping from S to S prime, right? So if F prime F inverse is a biholomorphic map, then you are saying that S prime, F prime, and S and F, these two pairs are same. You have same Riemann surfaces. So this gives you, under this equivalence, you have an equivalent class of pairs, which I denote by this. So the definition of Riemann surface is that you can consider all possible such quasi-conformal transformation. Then the Teichmuller space R is the equivalent class of all these pairs, all possible pairs. So using quasi-conformal transformation, you can define what you mean by Teichmuller space. And this is the definition that we are going to use. And we will see that once you transform this definition to the Fuchsian model, this becomes extremely powerful.
Teichmuller space is space of conformal of a complex structure.
Exactly, yeah. But some of the complex structures might be still same, using large diffuse. Yeah, it's actually classes. It's equivalent classes. So here I should say that I am considering only small quasi-conformal transformations that can be related to identity. So I am just
In the neighborhood of the circuit are the darker.
yeah, yeah,
The variety of R.
exactly, yeah. So you start with the base point. Now in general, mathematicians have proved that this definition is true even if you vary the base surface. For us, okay, this looks obvious, right? All points to the modulus.
Somewhat constrained.
Yeah, so yeah, that is true.
But in the segment,
Yeah, so this is, I think, theorem by Teichmuller. So all these statements can be proved. There are rigorous proofs, which I don't want to even.
Is the space of complex structures, is it connected manifold?
Teichmuller space is, yeah, it's a connected manifold. Yeah. That's why we can parameterize them using continuous variables.
And Abhijit, why do you feel this? Why do you say it's transferable that it is? I thought these were all general maps that were oriented.
Exactly, that is true. So the condition of quasi-conformal transformation is just putting you that slight
So
constraint.
Jacobi is going negative somewhere, which is the.
Right, but is it that all coordinated trilogy maps are constant?
I thought.
Yeah,
Why not? I mean,
I didn't put any.
No, if K goes more than one.
Then it can change
Good
that.
for us.
Yeah.
The Jacobi version.
There could be these maps where K goes approaches one
I
as a
Also, these are all done batch-wise, right? I mean,
Yeah.
So it's still not so clear that, you know, you can change topology, you can add functions.
It cannot change topology
So this is
within one particular. Yeah. So Teichmüller space is defined within a particular
one
topological class. Yeah. Yeah. Even moduli space is defined within one topological class.
So you keep taking the same chart for everybody just to simplify.
Yeah, you can do that. You can do that.
Like the complex structure for Tor.
That is true. Yeah. So now, one other aspect is that we said that we can always find a universal covering for Riemann surface R and S. So provided you have a quasi-conformal transformation from R to S, so you can lift that quasi-conformal transformation to R tilde S tilde with your yes, say let's say G, with a quasi-conformal transformation on that simply connected domain. So this is the power of universal covering. So you see, to study the quasi-conformal transformations on a complicated Riemann surface is still difficult. So you have to look into all patches, and then it's extremely difficult. Things are not very suitable for doing explicit calculations. So now you are using the idea of universal covering. So universal covering allows you to lift the quasi-conformal transformation to a simply connected domain. So at the end, we are going to worry only about quasi-conformal transformation that you perform on upper half plane.
And so then there's no patches there. Just
You don't want any patches.
Yeah.
Right. So that's why covering is the thing which is doing all the non-trivial thing. Yeah, so I have to tell you what, I just said that I can lift it. Now, how this is going to play a role in the case of Fuchsian model, that's what I'm supposed to define. So there also I will state so many results, because to prove all of the results, I think I require 1 or 2 semesters, which I don't want. No, there are no obstructions. Yeah, because we saw that if I restrict my covering map to some connected domains, then these are biholomorphic. So I can always lift them.
You're going to say this, but just carry Abhijit's question. Given a certain identification group, that will give you restrictions of what kinds of X you can set.
Yeah.
So not a bit. Just have to figure out.
Yeah, yeah. So in fact, you start from some random quasi-conformal transformation on the upper half plane, then you can make it into a quasi-conformal transformation that is a quasi-conformal transformation on the Riemann surface by using the trick, the so-called trick, by taking the point crescent. So which I will, is like image, exactly, is simple.
You make it periodic.
We make it periodic, exactly. So now I can define something called Beltrame differential. I mean, it looks like there are so many definitions, but at the end, the good thing is that we will get something which is explicit. So that's the reason why I'm going through all this different nomenclature.
It's totally great for us. I mean, I've heard many of these definitions and never understood.
So let me define Beltrame coefficient or Beltrame differential. So it's defined as a ratio. So you have a particular quasi-conformal transformation f. For that f, so now I'm just assuming that f is a quasi-conformal transformation that I perform on a simply connected domain. So mu f is defined as the ratio between del f by del c bar and del f by del c. So if I compute the Beltrami differential for a holomorphic map, is 0. No, I don't want mu f to be constant, but the condition that I put is that take the domain D, and then I can evaluate mu f at every single point. Then the maximum value that I can get must be less than 1.
Right. And if I wanted to look at infinitesimal quasi-conformal maps,
Yeah,
then I can just take z is equal to z plus epsilon of
exactly.
z.
Yeah, that is yeah. In fact, I will compute the explicit Beltrami differential in the case of
This is the
twist
form
length.
which is
Yeah. Yeah. So now the good why I am interested in Beltrami coefficients. It just looks like a definition, right? Now this is actually very powerful. You can inverse the story. So provide if you provide me a Beltrami differential on a domain, then I can find a particular class of quasi-conformal transformation. So there is a general theorem that states that. So this is the yeah. That states that if you have a Beltrami differential mu defined on a domain or upper half plane, because that's the thing which we are going to discuss.
Definition is that it's function of z or it's maximum of?
No, it's just this ratio, just ratio.
Function of z and z.
Exactly. So it's mu c. So given a mu, a quasi-conformal transformation on upper half plane or some other or on complex plane, then the theorem states that there exists a quasi-conformal transformation del f by del c bar mu del f del c with and this quasi-conformal transformation that I can find by solving this equation will be unique, provided I give a normalization for f. So if I demand that f of 0 is equal to 0, f of 1 equal to 1, and f of infinity equal to infinity, then the relation between mu and f will be 1 to 1. So such quasi-conformal transformations are called canonical QC map. So for each Beltrami differential that you define on upper half plane, there exists a unique canonical quasi-conformal map.
So f of 0 equal to 0 means f of 0 comma 0 is 0 comma 0 and f of 1 equal to 1 means 1 comma, because these are functions of both z and z bar.
Yeah, so I can look into upper half plane and then I have c equal to 0 means c equal to 0, so c bar equal to 0, right? So I can think in terms of x and y. It's just make c real and then 1. So it's just substituting the value of c.
I mean just
Yeah. Exactly. Yeah, that is true. So it removes all those ambiguities. Now, given that
But
you
moreover, is it the case that if you don't fix this normalization, then the class of solutions that you get are related to each other by
some conformal transformation.
Not-
Yeah. Not another quasi-conformal. Yeah, that is true. It's not
Same
different.
class.
Exactly. So this normalization provides me a rule to pick up one representative from the class. Yeah. Give me a should be less. 1. Yeah. There is yeah. Normalization. Exactly. Yeah, that is true. So now why I use that? So I use canonical quasi-conformal transformation to define the strictly less than 1. If I, I can define the Teichmuller space of Fuchsian models using this notion of canonical quasi-conformal map. So I can replace Riemann surface with the associated Fuchsian model gamma. So the definition of this Teichmuller space is the following. So the uniformization theorem says that T gamma, which I will define, is equivalent to TR, the previous definition. But gamma is the Fuchsian model, so R is equal to H by gamma. So it's a group, Fuchsian group associated with. So what we are supposed to do is, on the upper half plane we consider a group QC gamma. So it's the set of all canonical quasi-conformal maps that you can define on H, such that so you start with a group gamma and then perform a quasi-conformal transformation that belongs to this group. Then if that quasi-conformal transformation has to belong, if that quasi-conformal transformation wants to belong into this group, then it has to do the following things. So you take the quasi-conformal transformation and act on the Fuchsian group, then you should again produce a Fuchsian group. So omega W gamma of W inverse must be a Fuchsian group. Oh, it just means set of is quasi-conformal, set of all quasi-conformal transformation. QC is just quasi-conformal. Yeah, it's just a nomenclature, QC gamma.
QC of gamma is a set of all
Canonical Q. So here I define, I use this notion, canonical quasi-conformal map.
Okay, and canonical means you are defining it.
Yeah, defining, it satisfies this normalization. W0.
Oh, I see. Canonical is a number.
Yeah. So then I can take this quasi-conformal map and then act on the upper half plane. That will give me a new Fuchsian group, new group, which could be Fuchsian or anything else. Right? It could be
So mu is just
mu can be complex. Yeah, mu can be complex.
so less than 1 means mod less than
Mode you should be less than 1. So I can take the canonical map and then act on the Fuchsian group. Then I should be producing another Fuchsian group,
Well, Fuchsian group was what? Some subgroup of SL2.
some subgroup of SL2.
Any subgroup.
Yeah.
Okay.
So that means it should not be some random complex subgroup, right, of Mobius transformation.
Meaning, and is it, if I just give you any subgroup of SL2 and called Fuchsian, or there's some model?
Naively I can think that that's if it's a normal subgroup, then of PSL2 that should be a Fuchsian.
Any subgroup.
Yeah, any subgroup.
Okay, there is no restriction to be discrete.
No, it's actually continuous group.
So this is the condition for the existence of some kind of a commutative diagram in which H goes by quasi-conformal transformation to H here,
Yeah.
and then you go down
Yeah.
by a quotient to some R,
Yeah.
and then you apply this quasi-conformal transformation here as well.
Yeah.
That thing.
Yeah, thing. Yeah.
And then whatever you get this animal on the this lower right,
Yeah.
some S,
Yeah.
and that should be some quotient.
Exactly. Yeah, some portion. Correct.
H.
Yeah. So you don't want to destroy your Fuchsian model structure after performing this quasi-conformal transformation. So all such quasi-conformal map forms this group, and then the definition of Teichmüller space T gamma is that.
Can you read that equation?
So it's Fuchsian. It should be a Fuchsian group.
Fuchsian group meaning element of the same Fuchsian group.
No, it could be another Fuchsian group. So it's a different. Yeah, it generates a different complex structure. You get new Fuchsian group.
So you restrict your canonical map such that it produces.
Exactly.
You
Yeah.
do not restrict the Fuchsian element.
Yeah, that's true. So you start from quasi-conformal transformations and then look into a particular class of quasi-conformal transformations that will keep gamma even after performing the transformation a Fuchsian group.
This I'm not understanding. You're not asking about Fuchsian.
Oh.
You start with a group element, this will all,
Yeah, so always
yeah.
because omega cancels, you get gamma.
The group structure will be preserved, right?
No, so that the structure will be same, but if you want, you want that the elements of this group should be real, right?
Real. So that's real means what?
The elements should be
As SL2R matrices.
SL2R matrices. It should be,
Right.
yeah,
Right.
because it's a subgroup of PSL2R, right?
Fine.
Now I can generalize this notion.
And how did you find what this omega was?
Omega. So you can just this is a random canonical transformation. you can start from a Beltrami differential, and if so now I'm looking into all possible Beltrami differentials that I can define on the upper half plane, and then use that Beltrami differential to compute the canonical quasi-conformal map, and then see how that quasi-conformal transformation is transforming the Fuchsian group. Right? It's like a series of
I understand in principle it's there, but is there a practical way of
doing it.
yeah?
How do you solve for that class of omega?
Well,
That's
given a quasi-conformal transformation changes the complex structure.
yeah.
Now I want to know what is the change in gamma that will generate this new complex structure? How do I solve that question?
Yeah, so that's the next thing. Yeah. So this is another abstract definition. So this is the way.
Okay.
Huh?
That, so this omega, gamma, omega inverse will not be part of PSL2 anymore in general, right?
In general, no.
I mean, not even PSL2C. I mean, it's a,
Oh,
Because
because it was
the omega is an arbitrary transformation, right?
Yeah.
So it's in general very complicated map.
Yeah. So, but I'm putting a particular condition that I mean, if I want that to, I mean, if I want that particular canonical QC map to belong to a class of canonical map that I am considering, after the quasi-conformal transformation, I should reproduce a Fuchsian, another Fuchsian group.
Sorry, completely missed this.
Yes.
My understanding was that you, which is wrong, is that you use this canonical
Quasi-conformal map.
to generate a new complex structure, and then you ask which new subgroup of SL2R would generate this new complex structure.
Yeah. So
That's
so
what I thought you were
that,
saying.
so
But then what is this omega?
So omega is just, maybe I should not have introduced this. Maybe I should have directly gone to the final definition. See, so the point is that maybe I can provide you the practical definition that you can use.
Okay, go on.
Yeah. So the
using omega to get another
another group. So it could be something called quasi-Fuchsian group, like which is a generalization of Fuchsian group.
But the complex structure is the same.
No, the complex structure will become new. Like you use
On the surface.
on the
That's
surface.
Because the group will change.
Yeah, that is true.
But as long as it is embeddable in the SL2R, then you are fine.
Yeah.
That's this condition.
Yeah, that is true. That is the no. It could be that I mean, you are producing some trivial transformation.
For what I was interested in, I mean, the new subgroup of SL2R,
Yeah.
that would not even be a similarity transform, right?
Yeah.
Because it would be genuinely new group.
That's true. Let me give you that that definition.
That's for the same.
Gamma is a
For in order to produce the same
Yeah.
Is that
isomorphism, just like embedding
the
them.
major transformation will have
What
most
is the isomorphism?
Yeah,
will give you
No, I
something different.
something different.
Will not be a rational function.
Yeah, that is true.
Only when you get a rational function with new coefficients, A prime, B prime, C prime, D prime.
Yeah, then that become a
becomes
exactly.
I missed this.
Very small.
Please say it again.
I say F is the transformation of the variable, while gamma is just a rational of quotient A, Z plus A. So in general, you make a transformation of the variable, you may apply F to the Z, yeah, you will not get a
That's
rational
it.
function.
I mean,
So
yeah,
only in
there
very
could be
few
quadratic
cases you will
cubic
get a
and
new rational function.
Yeah.
Those are the cases.
Only if F is linear, then you can have a rational fraction going to a rational fraction.
Well, you know, many other cases.
Something
We have considered basic level. In order to get the same topology, you would want the group that is generated, the new group that is generating this to be isomorphic to the original group, right?
Yeah,
Just the embedding to be different.
yeah,
Is that
yeah. So let me give you the precise, the practical definition.
Just to make sure, is this a case of are they isomorphic or not? Suppose you take two different subgroups of SL2R,
Yeah,
that as subgroups are different, they have different multiplication groups.
yeah, yeah.
Can they generate the same topology, different complex structures with same topology?
See, in the previous example that we had for the pair of fans, you see that you are actually not changing the structure of the group. You are just changing the elements, right? So you have a parameters within the elements, right? So you are varying the values of each
I didn't understand. You had some elements which depended on L.
L. Yeah.
And if I multiplied them,
The structure is same, right? So
what do you mean by structure is same?
you mean the from the point of view of homotopy, like you see that you have similar cycles, but what is the length of that cycle? That varies when you change the parameters, right? Or, that you use to define
Is
elements
there a
of
similarity transformation that will change L?
Well, another way of taking it is in order to
that. So that's
the discrete, we can just look at generators and derivatives. And those are without. They don't depend on it.
See, can I just ask a equivalent geodesics will remain the same. So you cannot do isomorphism.
So maybe I can give you the precise, practical definition. That will take away all those confusions. So the practical definition is the following. So the way, the thing that you can use for doing calculation, to do that you have to go for some other definition, more manageable definition of Tate-Model space of Fuchsian model. The manageable definition is the following. So you start with a Beltrami differential mu c on the upper half plane. Then you can use this Beltrami differential to define a Beltrami differential on the full complex plane by extending the definition of Beltrami differential in the following way. So you have upper half plane on which your Beltrami differential is same mu c, and in the lower half plane H star you define including R real line, you define 0 as the Beltrami coefficient. So this mu tilde c is a Beltrami differential on the full complex plane, including the infinity. So if I include the infinity here, then what I define is the following. So you can use this Beltrami differential to find a quasi-conformal transformation, which is a quasi-conformal transformation mu W mu on the full complex plane. On the full complex plane, now I can define a canonical quasi-conformal map, which I derive from mu tilde c. So now mu tilde c, W mu act on.
I'm sorry, I was taking out Roger again. Mu tilde z, mu z was defined on the upper half.
Upper half plane. I'm just extending the definition. Oh, H is the upper half plane.
So you're saying it is mu tilde z on the upper half plane,
Yeah.
0 on the lower half.
Yeah, 0 on the lower half plane, including the
Lower half.
yeah, maybe lower, upper. Yeah, okay. So including the real line.
Yeah,
Including the real line. That's why I'm defining a Beltrami differential on the full complex plane.
So it was a Beltrami differential defined on the upper half plane but happened to vanish on the
On the real axis and the lower half
then
plane.
extended to the
Lower half plane. Yeah. So this is the way I just define it. No, it need not be continuous.
No, it happened to be to vanish. Did that mu z happen to vanish on the
On the real axis, right?
Yeah. So it's continuous, but not necessarily different.
Include.
No, but
So
the
huh? Which,
Did it go from the upper thing?
Yeah.
Did it go to 0 as it reaches the real line or
no, I'm not assuming anything. I'm just assuming that mu c should be something which I can obtain from a quasi-conformal map, right?
but it need not be go to 0.
Yeah, yeah, that is true. So given this general, so given a Beltrami differential on the upper half plane, you can extend it to the full complex plane, including the infinity. So what you are obtaining is a Beltrami differential on the full Riemann sphere. Then you can solve this, use this extended Beltrami differential to find the quasi-conformal map, which I denote by W mu, and then I can use this W mu to change my Fuchsian group to something else, right? By performing a quasi-conformal transformation. Then,
This text,
Yeah.
why is it of this form? Why is it W mu?
so see the W mu acts on the complex plane like this, right?
But the mu, what is the W? What is the mu index?
Oh, it just denotes the which
Which,
corresponding to which Beltrami differential.
It's not a vector field.
It's not a vector field. I won't use any vector field in this. Maybe too much of fluid gravity. Oh, I see. Maybe it's more of mathematics.
Okay, and what is W? Is it an element of SL2R or not?
It's actually, you see, you take W mu and act on some element on gamma, what you get is an element that belongs to, that's a subgroup of Mobius group. An element that belongs to the automorphisms of Riemann sphere, which is actually an element of it's a Mobius transformation. It's not a real. I mean, it's not just an element of PSL2R.
I mean, gamma I'm thinking of is 2 cross 2 matrix. This is
Yeah,
okay?
that is true.
Can I think of W mu as a 2 cross 2 matrix?
Exactly.
Is this 2 cross 2 matrix SL2R? No.
It's actually PSL2C, I think.
But like I can think of it as 2 cross 2 matrix A, B, C, but like,
But W is not that way at all. You know, W is very like complicated. For example,
So WME is actually a function, right? It's a continuous function on the for full complex plane. Quasi transform. It's not a matrix, so it's just a notation.
Thank you. So gamma is sort of a function.
Yeah.
So this is a highly nonlinear function.
That's right. That's right. As a result, it's very non-trivial thing that this object is finally again a rational fraction, you know, of the form some A prime Z plus B prime divided by C prime Z plus B prime. This is what Ashok and Before.
Yeah, yeah. So that's why I'm restricting my all possible quasi-conformal transformation to something which I denoted by QC gamma, some special classes. Yeah, in which I am interested. Yeah.
So what kind of W is there? I mean, it's again some rational fraction or?
No, W mu can be something extremely complicated. I mean, which could.
But it's this thing W gamma W inverse is again a rational fraction.
Maybe it will be clear once I write down an explicit example, like when I give you a specific parameterization.
But just to understand, this whole thing is a function of Z.
Yeah, it's a function. Yeah, that's true. Yeah,
It's a function of
it's
composition of
composition, right? So it could be at the end thought of as some Mobius transformation. The transformed element will become a Mobius transformation.
I think word Mobius transformation I don't understand. Is it AZ plus 3 over 6?
Because you see, this is just yeah, that is true. Because that is the only possible diffuse on the complex plane, right? Up. No, yeah, it's PSL to C. It's more general.
To C, but not R.
Right. So you are extending your definition to the full complex plane. Now after extending your Beltrami differential, you find a quasi-conformal transformation, not just on the upper half plane, on the full complex plane, so that you have more possibilities. Now you are deforming your Fuchsian group to something called quasi-Fuchsian group, which is not actually a real, which contains complex elements. So now the good thing about this thing is that this function is that at one go you can do two uniformization, two Riemann surfaces. So the group so I denote this group by gamma mu. Now this omega mu transforms the upper half plane to something else, right? Which I denote by h mu. Yeah. Yeah, that is true. So I don't want to fix the real line. The most general case is that even the real line will fluctuate. It will become something else. So the only thing is that I will have a line that that separates the full complex plane into two. But it's not necessarily a real line.
Here we have restricted the W mu to be such that this W gamma W inverse is again subgroup of PSL.
No, it's yeah, PSL. That's a generic statement, right? No, I don't have to restrict anything. It's a generic statement. But the quasi-conformal transformations that I have, QC gamma, I mean, this Beltrami differential, see, omega mu is not completely general. It's a solution of this particular kind of Beltrami differential. Yeah. I don't have to put any further constraint. No, I don't have to put any further constraint.
I don't understand that. How could it be that you take sin h of something, do inverse of sin h, do linear transformation, do sin h again, and you get az plus b over cz plus c?
Because sin h, see that.
I mean, it has to be some special function.
No, it's at the end you will see that this is like some fractional functions. So if I find the some
Is it plus this thing, the Z is also different now. The Z is also a new complex number.
yeah, it's a new complex number.
I mean,
It's a transform thing. So maybe I think I mean example it will come later. So I just want to define something.
I just don't understand that. At the level of functions, it sounds take any random function, it will not work.
Then it
You
will
see,
be
actually I'm not supposed to take any random function.
yeah.
Well, I'm not supposed to take any random function. I'm supposed to take a solution of this particular object.
Whether we
But Rohit,
Huh?
that solution of the particular object is sufficiently generic, right? Because
Yeah.
the only some inequality that is imposed
That is true.
on me. Right?
Yeah,
So it's a very generic function.
it's a generic function.
Generic function will conjugate a PSL to an element
Yeah,
and generate a PSL to it, right?
that is true. So, but
It's not enough.
so the full object, full generic function, it should be a transformation of complex plane, the full Riemann surface to some other structure, right? Without actually changing the complex structure. So anyway, C bar has only one particular complex structure, right?
But why would it not take a complex structure? Because it's a function of Z and Z bar, right?
See, for simply connected surfaces, you don't have many possible complex structures, right? You can always find a conformal map that will take you to the original CC bar that you have. So that's the first result that I mentioned. For a simply connected surface, you don't have any non-trivial possibilities. You have one single complex structure. Riemann sphere is a simply connected surface. So that's the uniformization theorem.
Are you saying that
Suppose you
in
take
go on.
Z goes from, suppose the W mu is something like Z plus Z square plus Z bar square, right?
Yes.
Or Z plus Z square plus epsilon Z bar square, something like this.
Yeah.
And then if you carry out this transformation, it is not very complicated. I mean, I'm a little confused.
Yeah.
I mean,
Even if you take just conform and z going to z square,
Yeah.
what you will have is az square plus b divided by cz square plus e, and then you have to do square root back again.
Yeah.
That object is certainly not some a prime z plus b, right? I mean, you do this stuff, you take a square root now, and that's not a modest function.
yeah, but see, I mean, one thing I can imagine out of this constraint that if you take Z plus Z square, right, the direct derivatives are zero somewhere. I mean, I wonder if that is the point that we are,
Exactly. See, the del S del C bar, I want that that should have a nice behavior, right?
yeah.
At least as a real function of x and y, they should be continuous.
So are you saying, Ashok, that maybe it restricts it to linear functions?
No, Bhagya, one thing, I mean, if you take square root of Z bar plus Z square, right, that's okay. I mean, I shouldn't, I mean, it can't get restricted to linear functions. I mean, it should restrict to. Yeah. I mean, what I have some functions which give zero, but if you take square root of, add to Z some square root of Z bar plus Z square,
Yeah.
right, with an epsilon, that should be okay, I think.
In fact, the kind of example that I will explain, that has even exponential kind of transformation, but which are restricted to some specific region.
So, Z bar plus Z square, that's not what I was.
No, but will z bar plus a squared, I think is real. I think, yeah.
So maybe I think I just want to continue and give the definition.
Okay.
Because some of the results, I mean, even this next result that I will mention itself is something which I can't even give you an intuition why those things are true. It uses some of the, I mean, I don't see.
The question here, Roji, is more like what is true here? I'm not even understanding what the statement is.
Yeah, I haven't made a statement. I'm just going to.
No, you have made a statement.
So I'm just saying that I am. You see, I can always make a transformation on a complex plane, right? So omega mu c is some function, some quasi-conformal transformation,
Yes.
right?
Are you claiming that for every quasi-conformal transformation, omega mu, gamma, omega mu inverse is equal to an SL2C transformation? Are you claiming that or not? Yes or no?
See, the mu c that I am supposed to use are providing me must provide me those kind of quasi-conformal transformation that will make transform a Fuchsian group to another Fuchsian group, right? So that's the restriction with which I started.
Okay.
So I throw away all other possibilities, right?
So you do this operation and you demand
Yeah.
that you get.
So the Beltrami differentials that I'm supposed to use are only those Beltrami differentials that can provide me quasi-conformal transformation that belongs to the set which I denoted by QC gamma. So where I said that Fuchsian group should go to Fuchsian group. So here I am just extending that to the full complex plane, and then finding a quasi-conformal map on the full complex plane.
For the case of the torus, will it be only linear transformation?
A torus anyway I can't really.
Or you can't do that?
Yeah. So anyway, let me continue. So there are some inputs which I already gave by definition, which will throw away some of the non-trivial possibilities.
Will this be a finite dimensional set of omegas?
Oh, actually, yeah,
Finite. The number of parameters in mu.
yeah, it will be.
satisfies
Yeah,
with
definitely.
Finite dimension.
Yeah, it will. It is precisely the one which gives you the Teichmuller space.
For a genus 2 surface, the number of parameters in that will be four
Yeah,
real
yeah,
parameters.
yeah, yeah.
Okay.
That is true.
Okay.
That's why it's finally giving you the Teichmuller space. So see, I can start with the special class of conformal transformations that or Beltrami differentials, and that will provide me another quasi-conformal transformation on the full complex plane. Then I have to define. I see that the upper half plane will be mapped to something else under this map, which I denote by h mu. This may not be the boundary of h mu may not be real axis.
But there it was.
Yeah. In the previous case it was.
It was.
Yeah.
It was real.
Yeah.
Now if you continue and you find that it might.
Yeah. It could provide. It could take real line to something else. And then the lower half plane also will go to something else. Then the gamma mu that I can find can act on h mu and this will provide me a Riemann surface, which I denote by r mu. So because h by gamma was r, and h star by gamma is r star, where r star is just the image of r, by saying that the complex coordinate on r is c and the complex coordinate on r star is c bar. Let's say local complex coordinates everywhere. So you are changing at one go you have two Riemann surfaces. One Riemann surface is actually the image of another Riemann surface. Since now you are looking into the full complex plane, not just on the upper half plane. So such moduli space or Teichmuller space, right? So I have to construct the tangent space or the tangent vectors. So that is the final reason why I'm studying all this complicated stuff. Because the thing that you see in Polchinski, where he write down the measure, he says that you have to multiply Beltrami differential with B field and then get some form. So what he's multiplying is actually he's multiplying B with some tangent vector. So I have to explicitly find what is a tangent vector in general. So that is the reason why I'm going through all these funny nomenclatures and some definitions. At the end, I will get something explicit.
I see. And in the case that this is an SL2R element,
Yeah.
the SL2R element is not, in the sense of matricing, is not a similarity transform of the original SL.
Yeah, it's not simple similarity.
It's not a similarity transform in the sense of matricing.
Yeah, that is true. It's just these are functions. Functions are inducing some new transformation.
Right.
So since anyway, W mu itself is not a matrix, right? It's a complicated function. It may not be a linear transformation.
Why is gamma acting on H mu? I mean, if there is no constraint, it will mix H mu and H star mu, right?
No, the point is that the Beltrami differential at the lower half plane is 0.
But the gamma is not insisted to be element of SL2R.
No, gamma mu. Gamma, to begin with, gamma belongs to PSL2. Gamma mu is not an SL2R
Why
element.
does it take the image of the upper half?
See, it's just
Image of the upper half plane, not the upper half.
no upper half plane.
Just any
It's just anything.
H mu.
H mu is not upper half plane. The boundary of H mu is something which is not real line, which could be real line or which may be something else also.
Because gamma mu is just projected like this to
By gamma mu. So I say that omega mu and omega nu are giving me same complex structure provided omega mu equal to omega nu on the real axis. This is something which I won't be able to prove now. It uses all the complicated some properties of Fuchsian group.
but it would be like omega, this composition would be holomorphic, then it would be a thing. Is it the same as that?
See, the quasi-conformal transformation is on the upper half plane, not on the. It induces a transformation on the complex plane, on the Riemann surface. So, a priori, I don't think I can just make in a random statement.
Basically, there should be a biholomorphic map between the two.
I mean, the quasi-conformal transformation that is induced on the Riemann surface by omega mu and omega nu will be related by biholomorphic transformation. So, how will I state on the upper half plane or on the complex plane?
That will translate to this condition.
That will translate to this condition. So, this condition means that the group gamma mu and gamma is exactly equal to same provided omega mu is equal to omega nu on the real line. Now, further one can show that omega mu equal to omega nu, if this condition is true, then omega mu Yeah, on the lower.
Yeah.
Yeah,
okay.
lower.
So,
So let me continue. Like,
that before where you shoot it over that, so that
Yeah.
on the real axis.
yeah.
You're-
So see,
you're doing
so to make some so here why I am doing this, to make some statement on the Riemann surface, I am going for some image of Riemann surface and then stating some result on that image.
I think omega has to be continuous,
Yeah,
but not the differential, because the jump.
yeah, that is true.
The relative jumps at the real line.
Yeah, so
And the fact that provides a condition for this one to
on the real line. So on the real line, if omega mu and omega nu is equal, then the Fuchsian group that is generated after this quasi-conformal transformation is not different from the original one. This is the statement which I don't be able to prove. Right now, it can be proved, but I mean it takes some time. And then if omega mu equal to omega nu on the real line, then on the lower half plane omega mu and omega nu is same. That means on surface R star, the image omega mu and omega nu are exactly same. It's not that omega mu and
elements in their algebra. In particular, you can talk about generators and the relations between them, and that will define your group.
that is true.
Right? So is that group is the
But
same?
so the point is that even for the pair of spans case,
Yeah.
even if you vary the parameter L1 and L2, the group structure will be same, right?
Group is the same, right?
Group is the same.
And just to understand that completely, are the 2 cross 2 matrices similarly transformed with each other? Is that an operational version of your
Sure,
code?
yeah. It does look likely to be. That's some very complicated signing here. Question.
Oh. Okay.
So as you said that the group that you wrote down,
Yeah.
gamma 2,
Yeah.
gamma p rather,
Yeah.
yeah, it doesn't have 1 and del p.
Yeah.
As you change this to alpha and so on, are they related by similar terms?
No, I don't think I can find any.
But what do you mean that the intrinsic structure is the same?
I mean the multi. I mean, why I should be really bothered about that? In my situation, what is the implication of having a similarity transformation for this situation?
In order to show that the group are, the two groups are isomorphic to each other for different values of L.
To me, it looks like okay, you are getting different representations of the same group structure, right?
What does that mean? Does it mean that the group elements are similarity transformed? You can go from one end to the other
I think, I mean, in general, it might be possible that 2 by 2 matrix with some n. So I'm, so I'm not, so the
Some discrete points, right, in the space of groups. How are you moving from those in continuous way?
so you see, I have,
There is a continuous family of discrete things.
yeah.
Is there?
I don't know.
So the one which I wrote is explicit.
Sounds very.
What about rotations? Rotation by an angle theta, by multiples of theta.
Yeah, yeah,
As I change
yeah.
theta,
That is
it changes the-
so. It's precisely that. I mean, that's an example of an even more simple situation.
No, that's
You're the same you want. Which has the similarity transformative.
Yeah.
So he wants to say that as a model.
It's true.
No, I mean, the same group also means embedding in the same.
As a mathematical object, it's very different. As a group.
So I think, I mean, it depends on what. So maybe I should go. Yeah. Yeah. So the point is that here it's not whatever I stated now. It's not some definitions. I said that I start with a Beltrami differential on the half plane and then use that Beltrami differential to define a Beltrami differential on the complex plane. this should be
So on the real axis, z minus z bar 0, so z is going to z.
here.
So this is an example.
I mean, is it clear that this is part of this QC comma? Because does it, when you conjugate a PSL2C element, PSL2 element by this, does it generate a PSL2C element? It's not completely clear to me that it does.
So maybe I think these are things which maybe I will try to answer tomorrow. So let me continue.
So you're
Otherwise,
saying
I'll
the
just
part
stuck with
that's
you.
not clear is that the determinant will be what?
That when you conjugate a PSL2C element, it should give you a PSL2 element, it should give you PSL2C, right? That's one more.
Yeah, so the statement is that this new group that I am getting here in this picture is not Fuchsian group again. It's something more general.
Yeah, exactly.
So that's what I said. It's called quasi-Fuchsian group. I mean, which is not defined using the usual definition of Fuchsian group. It's a
Having one example would be very, very.
So the point is that most of these things are extremely, I mean, abstract statements. Maybe I will give you an example in a special case.
Just
So
any example, the simplest example.
I will work out. I will work out this for a particular case. I will work out the Beltrami differential and then find the tangent.
And we'd like to see that this omega preserves this form. transformations, it may be hard to solve that condition. But for infinitesimals, it should be easy.
Yeah, I will give you an example of quasi-conformal
But I should
transformation.
just be able to solve it, right? I just say z is equal to z plus something small.
That so
Linearize it as something, I'll get a condition. I'm sure I can solve that condition.
you can solve it. Yeah, right.
Can you tell us what the answer to that condition?
Uh,
For string theory, you only need infinitesimals.
exactly.
So infinitesimals are important also for physics.
That is true. So and the point is that if I do some random transformation, and at the end I want to do something useful, so that it generates a Beltrami differential for quasi-conformal transformation that I perform on R in using a quasi-conformal transformation that I perform on R star. So here I realize that if two quasi-conformal transformations are equal on R star, then that they are able to give you a nice result, which utilize the fact that C star has some nice property. The full complex plane has nicer properties than upper half plane. So that's maybe that's one intuition why they want to include the lower half plane and real line. So the compactified
Gamma now, this is gamma.
oh gamma acts on gamma is an element of that belongs to Fuchsian group. So gamma C is like
Gamma is a 2 cross 2 matrix.
exactly
Or it's AZ plus A plus B plus.
exactly that's the thing. So
It's a holomorphic function.
exactly it's just a by moding out with gamma. That is a simple definition. So this is the definition of quadratic differential on H with respect to gamma. Quadratic differential that I can obtain from the quasi-conformal transformation. Now the good thing is that if omega mu is not a non-trivial quasi-conformal transformation, of this kind that I can write on the lower half plane gives me the space A2 H star gamma, and then I can identify H2 H star gamma with the Tek-Moore space P gamma. Then if mu and so let's consider two Beltrami differentials mu and nu, which is acting on the Riemann surface R.
Okay.
So now I want to know whether mu and nu R star, and if I get different phi mu and phi nu, then mu and nu is providing me different complex structures. So that means I can identify the
Phi mu of Z is a holomorphic.
So the point is that C is not actually C must be the C that is on the lower half plane.
That's what I said before, that you
Lower half plane, right?
What is the constraints on that? Is this constraint that it remains an AZ plus P over CZ plus D?
So the statement is that if mu was given
Define what is happening in the lower half plane
yeah,
as an identity function,
yeah,
and it defines what is happening in the upper half plane
yeah,
as the deformation.
exactly, yeah, yeah. Said that I start with a new definition which is more easy to handle for doing explicit calculations. So the other definition is again giving me a character.
Mu need not be continuous on the lower half plane, but omega must be.
that's
Yeah.
what I said, yeah.
So
Otherwise, there is no relation between what happens in your
yeah,
class.
so that's why. Point is that you have the infinity also, right?
It is,
So you want nice function, right? That behaves
like,
even if the Anyway, I just started looking into these things only few days back.
What is not clear to us is how he means.
Yeah. So given this, I with this connection, I think it's an important thing.
Using lower half plane very heavily.
Highway, that's why. So yeah, this is something which okay, as connection. Yeah. So first of all, you have to identify this itself. So so the like Naveen was saying, now since I have identified type inverse space with a so just some partition function and all, you can just get this. That's why physics is really surprising. Or
Sure,
even
sure,
if you
there's much more here.
exactly.
Complex such smaller space of a D.
You have quadratic differentials on R star that that can be identified with the type. with the complex structure. There is no quadratic differential. Uh, Beltrami differentials that I define on upper half plane by Bh gamma. Equivalence class. So here I have one-to-one space which I denote by harmonic Beltrami differential. H phi mu c and then take a complex conjugate. This since after taking the complex conjugate, this C belongs to the upper half plane. Beltrami this space
Wait,
will.
I thought that's the form. I thought it was a quadratic form.
It's not. It's a. This is a quadratic. Yeah. That's true. This is actually coming. So that. scholars.
No, but in where does the upper half lie?
Sir, isn't a condition that provides you non-trivial expression. You will make sure that if mu is of is actually null vector. So
Roji, any chance you could do this next time?
Yeah.